All right, let's start. Just a reminder about a couple of things. You might have seen that there was an announcement about the exam on Canvas. So, I mean, there is an announcement posted with the details of logistics for the exam, how it will work, etc. And there is a mock quiz. Doesn't have any mathematical content, but you can practice sort of just how the system will work, how to upload your solutions, how to sort of take a timed quiz, etc. So you can take a look at the assignment section on Canvas, just a reminder that the homework is due on Tuesday next week. So yeah, make sure you leave enough time for solving the homework, and let me know if you have any questions. As usual, I'll be available after the class, and also sort of all of us have office hours and so on. An announcement just regarding the logistics of office hours and discussion. So Tushant posted that some things were switched to Zoom, just to sort of avoid confusion. Seems like Gather was not working well for everyone, so we'll just switch everything to Zoom. So you can just find the links on Canvas as usual, but all office hours, discussions, and lecture, everything will be on Zoom. There will be a different link for the lecture and different one for the office hours, and then you can see the links on the Canvas calendar and just use it. So we'll just switch everything to Zoom, and then we'll also post an announcement about it. Okay. Yeah, it seems like Gather was a bit inconvenient for some people, so let's do that. Okay. Getting back to singular value decompositions. So let me recap what we did last time. Today we'll continue with this theme of applications of linear algebra. We'll see a few more, and then we'll continue this in the next lecture. And after the exam, we'll start with the second half of the course, which is related to probability. A recap of what we talked about last time. So we discussed singular value decomposition, or SVD, and for a linear transformation between two finite dimensional inner product spaces, which I'm not writing out the full statement here. It's a nice way of understanding the action of this linear transformation in terms of this kind of orthonormal set of vectors v1 to vr and w1 to wr, respectively called the right and left singular vectors. And you can write it as a sum of these simple transformations, or outer products, where for a vector u, each term just takes its inner product with vi and multiplies it by the vector wi. So, or if you write it as a linear combination, if you complete the v1 to vr to a basis for the space capital V, then all the linear transformation does is just kind of replace a vi by a sigma I wi for I from 1 to r, and for the rest of them it's just 0. Okay, so whichever way you want to think about it, these are almost like eigenvectors, and then they kind of give you a similar ease of working with a transformation. We also saw the matrix form of it, where you can write any matrix A as a product of three matrices, and the first one has R orthonormal columns. I mean, we saw a couple of different ways of writing it. One way is you have R orthonormal columns. The second is a diagonal matrix with entries sigma 1 to sigma r on the diagonal. And the third has R orthonormal rows, or you can think of it as a conjugate transpose of a matrix with R orthonormal columns. Okay, and we also saw there is a slightly different way of writing in terms of unitary matrices, where you sort of complete these orthonormal columns to a basis for each of these spaces, and yeah, you get yeah, a slightly different form of this. And we also saw that this decomposition, in addition to kind of giving us a way of working with the transformation, is also useful for solving some sort of computational problems. And one which we saw was coming up with the best low rank approximation for a matrix. And rank here is used as a measure of how simple a matrix is, because rank is just the dimension of the image. If rank is 1, it just means that the image is one dimensional, or it lies just in a small subspace. So any output this matrix gives you is just a scalar multiple of a vector, which maybe is the basis for this one-dimensional space. And in general, low rank matrices are thought of as maybe in some sense low complexity or simple matrices. And this is about approximating any arbitrary matrix with a low rank matrix and understanding how much the error is going to be, at least in one notion of error, which we defined last time, which was the so-called operator norm or spectral norm of a matrix, denoted by this symbol for this matrix A minus B. And this is just the ratio of the norm of A minus B what happens to a vector after you apply the transformation versus its norm before, and you maximize over all non-zero vectors. So just exclude the 0, 1. And we saw that singular value decomposition, in fact, it gives a very simple way of computing the best approximation. It's a sum of R terms, just to take the first k ones corresponding to the k biggest singular values, and just leave out the others. Any questions about this before we continue? Okay. In the homework, you will see one other notion of approximation of a matrix by a low rank matrix, or trying to find a simple matrix which kind of captures in some sense a given matrix A. And if you can always ask me if something is unclear there. Okay. And I mean, a very related notion of approximation is what's called least squares approximation of a given data set. So this is also called dimension reduction. It's one of the ways of doing dimension reduction. In general, dimension reduction corresponds to this problem that you are given, let's say, data points in some high dimensional space. So let's think of this D as high. And you want to kind of find some low dimensional representation of this data for whatever reasons. And in general, a lot of algorithms behave better when your data is low dimensional. They can reason with it more efficiently. They can work with it more cleanly. And it turns out that surprisingly often data in high dimensions can actually be thought of as data coming from some, and this can be, this low dimensions can correspond to parameters of your model. They can correspond to some sort of geometric way of viewing data, whichever your application demands. So one specific way of posing this problem, and again, this is by no means the only one, is to say we are going to find a subspace which is of low dimension. So we want to think of it as low, such that it sort of fits the data in the sense that the square distance of any point from this subspace, or the sort of total square distance of all points from this subspace is small. Okay. And this you can think of a generalization of finding a line which represents points in 2 dimensions. So if you have points in 2 dimensions and you find the best fit line, what you are saying is that these data points in 2 dimensions, you're trying to represent by a 1-dimensional subspace, which fits them best. And this is a generalization with points in d dimensions and a k-dimensional subspace. Okay. Any questions about the problem before we continue? Okay. So, and yeah, I claim that this can also be solved using the linear algebra that we have seen. In particular, actually, this is just again a twist on singular value decomposition, but we'll see how it solves this. And this sort of reasoning will also come up in the homework problem on Frobenius norms, etc. Okay. The first thing I want to do is to define this problem more clearly. So actually clarify what we mean by a distance of a point from a subspace. And yeah, in sort of this geometric picture, it kind of seems intuitive that you sort of drop a perpendicular from a point to a subspace and then calculate the length of that perpendicular, or this sort of green lines. But in some sense, when you have a high dimensional space and possibly even a general inner product space, it's not clear what kind of dropping a perpendicular means, and actually how do we compute this distance given, suppose we are given some way of thinking about the subspace. Let's say we are given a basis for the subspace and we are given these points. How do we actually compute this sort of distance? And first, let's just clearly define distance. And so I'll define it as the distance of a vector v from the subspace S is just the distance of the vector from the closest point in the subspace. So I'll minimize over all points in the subspace of the distance between u and v. And whichever is the closest, I'll choose that u and call that the distance of v from the subspace. This can be used more generally. So this notion of distance can be used even when you're defining the distance of a vector v from any kind of geometric object. It can be a convex body, it can be a weird surface. It doesn't have to be a subspace, but it has a particularly convenient form for a subspace. Okay. And now let's get back to the question of computing it. So to compute it, we have to sort of understand how we specify the subspace. So suppose we are given an orthonormal basis, say u1 to uk for the subspace. Okay. Then I claim we can actually compute this distance in a very nice way, and then let's see how. And to compute it, I will actually compute the square of this distance. I mean, yeah, minimizing a distance or minimizing the square of the distance are equivalent. And I claim you can write it in terms of the basis very nicely. In particular, what you get is and you can also view this as Pythagoras theorem in some sense. It's just going back to our picture on the previous page. What we are saying is that you can write this distance in terms of sort of the norm of A minus minus the parallel component, which in some sense we are calculating in terms of these UIs. So and so the perpendicular component squared is equal to the total length minus the parallel component squared, if you want. But again, as I said, geometry can be difficult to think about, especially in high-dimensional spaces. So this is just a clean formula for computing it if you know a basis. I'll emphasize that the distance does not depend on the basis. So instead of W1, U1 to UK, if I gave you some other basis, W1 to WK for the same space, you could compute the same quantity in terms of if instead I had a basis W1 to WK. And they will be equal because both of them are actually computing this number, which has nothing to do with a basis. It just depends on the subspace. And as long as U1 to UK and W1 to WK are bases for the same subspace, they will give you the same quantity. These are just two different ways of computing them. They are not two different quantities. Okay. All right, now let's get back to computing it. So, and so we are given a vector V. Okay, before we go there, we are given a basis U1 to UK. Let's complete it to UK to UD, let's say. Which is an orthonormal basis for the whole space. Okay. Now, let's say our vector V can be written in terms of this basis. So let's say it's let's still use J. Okay. And any U in the subspace can be written summation just in terms of the first K vectors with some coefficients, right? And so V is given, which means C1 to CD are given. And we have to find the closest U, so we have to find B1 to BK. Okay. And so let's compute, and then we have to find the values for B1 to BK, which minimize the distance. So let's write down what the distance is. Okay. Let's write down what V minus U is. It's summation. For the first K terms, we get Cj minus Bj times Uj plus, for the other terms, we just get Cj. Because the B's only are coefficients for the first K, because U1 to UK are what span the subspace, and U has to be in the subspace. What we know about orthonormal bases and Parseval's identity by now, we can write the norm of v minus u whole square is as the sum of squares of all the coefficients, because we have an orthonormal basis. So we get okay. Now we are given C1 to CD, and we are free to choose whatever B1 to BK we want. Any guesses on how should we choose the B's so that we minimize this expression? Someone should speak up. It's okay, good. There is an answer in chat. Right, so we choose BI equals CI for the first K coordinates. And so if we try to minimize it over all U in the subspace, then we can choose all the BIs equal to CIs, and all we are left with is the remaining ones. Which can be written as the entire summation minus the summation of the first K guys. And now, again, what we know in terms of norms, this is nothing but the norm of V square. And each Cj we know how to compute. It's V inner product Uj inner product V for the first K of them. So I mean, it's just sort of stating what we know from Pythagoras theorem or from our intuition about projections to linear spaces in terms of an orthonormal basis, or giving us a convenient way of computing it. It's as I said, it's a quantity which can be computed in terms of the basis, but it doesn't really depend on the basis. And the closest point U that we found, where you just basically copy all the Cj's as Bj's, is also called the projection of the point V to the subspace S. And you saw orthogonal projections in the first homework and so on, and you can think why this operation is an orthogonal projection. So for a given point V, we find its closest point in S. This is some function. It maps vectors to vectors. You can check why it's a linear transformation, why it's a projection, in particular why it's an orthogonal projection, as we saw in the first homework. Okay, now let's get back to the problem we were solving. Here I've kind of omitted the absolute values on the inner product because we are over real spaces. So this is just, these are just real numbers. I can square a real number. Don't have to worry about the modulus. And I've just restated the problem as finding an orthonormal set U1 to UK, which minimizes this quantity. I'm going to think of the subspace S as being implicitly specified by these basis vectors. So you give me an orthonormal set U1 to UK, the span specifies a k-dimensional subspace. Whatever it is, I'll call it S. Okay. And we know that if we have an orthonormal basis for S, then this is the distance. So this is what we are after, which is the distance of AI from S squared, right? And on the previous page, we just proved that this is a way of computing the distance. So we are after this quantity. Okay. Equivalently, we can say we are trying to maximize whatever appears with a negative sign. So because this part does not depend on U1 to UK. So minimizing AI square minus some inner product square is equivalent to maximizing the inner product squares or the sum of those. And this we can write in a sort of slightly succinct way, which is easier to deal with. So let's think of a matrix in which kind of think of A's as column vectors, the data points, but we look at their transpose, write them as rows. And multiply it with a vector, let's say U1. And let's call this matrix A. Then the norm of A times U1 square under the standard inner product on R to the D, or the usual inner product, is nothing but the square of the first coordinate, which is the inner product of AI with U1. So A1 with U1 square. There's a square of the second coordinate, which is the inner product of A2 with U1 square, etc., and so on. So by exchanging these summations, we can write this quantity more succinctly as the norm of A times U1 square, A times UK. So now the goal changes to, so we have this matrix A where we kind of put in all our data points. We look at their transpose, put it as a row. That's just our matrix. And now the goal is, given this matrix, can you find an orthonormal set U1 to UK, which maximizes the norm of A U1 square plus A U2 square, etc. Okay. Again, this is a convenient way of writing what we are optimizing over, and slowly we'll try to kind of write it in a form where until we can use linear algebra, singular value decomposition, etc., to compute it. But this is just so far, all we have done is rewritten what we want to optimize. Any questions? Okay. Let's continue. So this is kind of restating our current goal, which is given a matrix. Now, recall that this matrix had n rows, and each row was the transpose of a d-dimensional vector. So I'm just going to think of an n cross d matrix, n rows, d columns. We are trying to find k orthonormal vectors u1 to uk, which will span whatever subspace we have in mind. And such that we want to maximize the norm of AU1 square plus AU2 square, etc. Okay? The sum of these all the way up to UK. And I claim once we phrase it this way, the solution is actually kind of easy to deduce from what we know about A. I mean, we'll prove that this is the right solution, but let me tell you what the solution is. The solution is just the right singular vectors. So all we do is take u1 equal to the first right singular vector v1. So A is a matrix. Any matrix is a linear transformation, and it has in particular right singular vectors v1 to vr, left singular vectors w1 to wr, and so singular values sigma 1 to sigma r, which we think of as being arranged in descending order. So v1 corresponds to the largest singular value, v2 corresponds to the second largest, and so on. And all we are going to do is take the first k of them, which are orthonormal, by the way. The singular vectors do form an orthonormal set, both left and right singular vectors. So here v1 to vr are in r to the d, w1 to wr are in r to the n, and yeah, so we want points in r to the d. v1 to vr is the set we should look at, and actually it turns out that you can just pick the first k of them, and that suffices. Now, a question about what happens when k is greater than r. And here, if k is greater than r, then the error is 0. Or you can check that the least square error is 0. That is, all points actually lie on an r-dimensional subspace. And you can think about why. But if they lie on an r-dimensional subspace and k is greater than r, what we are allowed to do is find a subspace of dimension less than equal to k. We can just output the subspace in which all points lie. And again, I claim this is not too difficult to see from the matrix, but you can think about it. Ask me if it doesn't make sense. Okay. Now, going back to what we were trying to solve, I claimed that if you take the right singular vectors in descending order of the singular value, take the first k of them, then that's the optimal solution, maximizing this quantity AU1 square plus AU2 square all the way up to AUK square. Another way of saying that is that for any candidate solution, the quantity we are trying to optimize is at most whatever it is for the solution which which is given by the right singular vectors. Okay. So let's first check what are we talking about here in terms of the objective, or what is it that we will actually get as an output. Okay. What is this quantity? Sort of norm of A times V1 squared. Anyone knows? You can also speak up if you like. It's, don't have to use the chat.
Can you say the question again?
Yeah, so I'm asking this A times V1 norm squared can actually be, we exactly know what this quantity is equal to. We know the value of this quantity. Can anyone?
Isn't it the sum of AI V1 squared?
Yes, so it is equal to summation over I inner product AI V1 square. But I claim we can also write it in terms of, in fact, very simply in terms of, let's say, the singular values. Yeah, that's a hint.
Sigma 1 squared.
Right. So it's actually just sigma 1 square, because the singular value decomposition gave us a way of, I mean, again, there are many ways you can compute this. But one way is that we know what the action of A is. You look at V1, replace it by sigma 1 times W1. Look at the norm of this. W1 is a unit length vector, so all you are left with is sigma 1 square. Same is true for all these quantities. So this is sigma k square. So the best we can hope for is sigma 1 square plus sigma 2 square all the way up to sigma k square. Remember, this is the kind of part that we were subtracting. So whatever will be left will be the error. And the largest thing we can hope to subtract is sigma 1 square plus sigma 2 square all the way up to sigma k square, where sigma 1 to sigma k are whatever are the singular values of this matrix. But if we know those, and yeah, I mean, that's a separate question, that there are algorithms for computing the singular value decomposition of a matrix, etc. But right now I'm just asking, suppose you know that, can we write down what this error is? Okay. And the way we will prove it is just by induction on K. So let's start with the base case, or we just want to prove that for K equals 1, it is indeed true that for any U, now U1 is an orthonormal set, which just means that U1 is a unit length vector. The norm of A times U, sort of A times U1 squared is less than equal to A times V1 square, or as we saw, sigma 1 square. Okay. And as before, you can deduce it in multiple ways. Let me give one. So let's write down the norm of A times U1 square as the inner product with itself. Let's use the fact that adjoint lets us move the vector to the other side. Or let me do it this way. And A star A or A transpose A are the same thing, because the entries of A are real here. And we're trying to maximize over, and this is nothing but you want the relay quotient of A star A computed at U1, we saw that the maximum value of the Rayleigh quotient is the largest eigenvalue. And the eigenvalues of A star A are sigma 1 square, sigma 2 square, and so on. That's how we define the sigmas actually. So it's just the largest eigenvalue, and the largest eigenvalue we already know is sigma 1 square. Another way of saying it is that we know that maximum over all u not equal 0, A times u over norm of u is the same as maximum over all u with length 1 of A times u. And we saw that this is the spectral norm which I assigned as an exercise last time, that the spectral norm is equal to the largest singular value. So this quantity is actually equal to sigma 1, and the square of it is sigma 1 square. Okay. And I mean, again, these are not two really different proofs, but the slight variations on the same argument. And I mean, you can also explicitly compute it by writing this U1 in terms of the orthonormal completion of the basis of the right singular vector. So yeah, there are many ways in which you can derive this. Continuing the proof, we want to now, let's say, assume for our induction hypothesis that the claim that V1 to Vk minus 1 maximize the sum sort of A U1 square plus A U2 square all the way up to K minus 1 is dominated by A V1 square all the way up to A Vk minus 1 square for all U1 to Uk minus 1. And now we want to say that if you add a term which corresponds to A times Uk norm square on the left side, then it's still upper bounded by if you had. So what we want to prove is that if you add A times Uk square here and A times Vk square here, then the inequality continues to hold. For starters, let's assume that the UK we are adding on the left side is kind of nice in the sense that it's orthogonal to V1 to Vk minus 1. It's orthogonal to the first K minus 1 of the right singular vectors. Okay. That's just, as we saw earlier, you can always define this kind of thing as a subspace. We define things orthogonal to one vector as a subspace. Here I'm writing something orthogonal to K minus 1 things as a subspace. Let's assume that UK is orthogonal to the first K minus 1 of the singular vectors. Then I claim that the computation is easy, or we're kind of done. So again, there are a few different ways of doing this, but so the norm of A times UK square is, I mean, if it belongs to the subspace Vk minus 1 perp, then it's upper bounded by the best vector we can choose in this subspace, which maximizes the norm, in particular, since UK lives in this subspace. And this can be, again, written as the best vector we can choose in this subspace. In a product of V times A star A times V. And it's a variation on the proof we did about sigma 1 square, that this is sigma k square. Okay. I'll let you think about this, but again, as usual, ask me if this is not clear. Again, you can write yeah, you can use eigenvalues, you can use properties of Rayleigh quotients, you can write this vector V explicitly in terms of the basis V1 to Vk completed to the whole space, whichever proof you like. So there are a few different ways of proving this statement. Okay. Any questions before we continue? Yeah, so today's lecture, strictly speaking, is not on the exam. I said syllabus for the exam is lectures 1 to 7, but do try out these exercises. This kind of manipulation is something useful. It is just a generic way of using an orthonormal basis and its connection to eigenvalues, singular values. And it's kind of, yeah, something which comes up all the time in applications of linear algebra. And finally, let's get back to justifying this assumption that we made that UK lies in this space Vk minus 1 perp. I claim that this we can do without loss of generality. So formally speaking, given any vectors u1 to uk which are orthonormal, uk doesn't have to be in the space Vk minus 1 perp. But I claim that we can construct vectors u1 prime to uk minus 1 prime, or sorry, uk prime, where now the prime vector, the uk prime, lies in this space, and they have the same span, they kind of give you the same subspace, and the objective value of norm of au1 square all the way up to auk square is the same for both of these sets of orthonormal vectors. So without loss of generality, if we are given u1 to uk, we can prove our claim for u1 prime to uk prime because the value of the objective is same for them. We will have also proved the inequality with this term on the left if we prove it with this term on the left. But when we work with this term, we have the nice property that uk prime lies in this space, and so our proof works. Any questions about the statement of this claim? We'll prove it in a minute. Okay, and the proof is actually sort of that we will try to only ensure the first two properties. The third property will be automatic, and we'll see in a minute why. Or actually, yeah, it's just the fact that the distance of a point from the subspace doesn't depend on what basis you choose, and this quantity is nothing. If you remember how we got to this quantity, it's just the sum of squares of distances or subtracted from the length, because this is what we got when we were looking at sort of the negative term in our expression. And as long as the subspace S spanned by u1 to uk and u1 prime to uk prime are the same, the distances are the same, and so these quantities are both equal. It doesn't matter as long as they span the same thing. So all we need to worry about is saying that there exists u1 prime to uk prime which are orthonormal and span the same set as u1 to uk. Additionally, uk prime lies in this special space vk minus 1 perp. Okay. And the proof is just sort of following the intuition that once we have an orthonormal set, we can complete it to a basis for whatever space we want. And here, it's just that we want UK prime to satisfy some conditions. So let's first choose UK prime. Okay. And we want UK prime to be in S, where S is whatever is the span of U1 to UK. Let's call that S. So we want UK prime to be in this span. In particular, we will actually require U1 prime to UK prime to span the same thing. And we want it to be in VK minus 1 perp. So let's see if we can find a vector in the intersection of these two subspaces. The dimension of S was K. The dimension of VK minus 1 perp, and this is an exercise, is D minus K plus 1. And that's something you should check. Again, it's related to problems or things you've already seen in the homework and some exercises you've seen. And we know that the dimension of the intersection of two subspaces is greater than or equal to dimension of the first one plus dimension of the second one minus the dimension of the total space in which they lie. This is something we also used in last lecture. Okay. And so this is at least one. So choose so at least one means that there is at least one vector here which is non-zero. So and if there is a vector which is non-zero, we can also divide it by its norm and get a unit length vector. So let's choose UK prime, which is in this. Okay. Since this is an S, we can complete it to an orthonormal basis UK prime. Let me write it backwards. So basically, you can complete it to a basis for the whole space, which you want, which is the space S. And then we are done. We chose UK prime to be, so the first property is satisfied because that's how we chose UK prime. The second property is satisfied because we chose U1 prime to UK minus 1 prime as a completion of UK prime to a basis of S. So of course, the span is S. They are the basis for S. And the third property we saw is just implied by the second property. So it's nothing new to prove. It's just it's convenient as an observation. But then we are done. We, without loss of generality, satisfied this extra property. And when we had this property, we already proved that the maximum is upper bounded by sigma k square, which is also what we added on the right hand side. This is sigma k square. So going back over our proof, what we did was by induction, we proved that for any U1 to UK, the norm of AU1 square to AUK square is upper bounded by the quantity we get when we plug in V1 to VK. And since our goal was to maximize this, we maximize using the right singular vectors so that they achieve the maximum value. And since the sum of squares of distances of our points from the subspace was exactly equal to the norms of the points minus the quantity we just maximized, we minimize the distances. And the way to minimize the distances is actually to output the space S, which is the span of the first k right singular vectors. So if you want to do this kind of dimension reduction where you want to minimize the square distances, there is a very simple way to do it. It's just that you look at the right singular vectors and output the space spanned by them. And this is going to be a good, or at least as sort of as good an approximation for the data set as we can hope for if this is the notion of approximation error, the square distances. Okay, and of course, there can be other notions of errors, and there can be other ways of optimizing. And this is a whole area. There are kind of many ways of dimension reduction. This is just one example. Okay. All right. Let's take a 2-minute break. Let's get some water, and then we can continue. Maybe you can also ask me if you have any questions or think of something in meanwhile. Okay. Any questions someone thought of about the part we just discussed? Okay. Let's get to another application, which is a fairly useful tool in terms of understanding matrices, eigenvalues, etc. So I said we can always maybe there are algorithms for computing a singular value decomposition, or there are algorithms for computing eigenvalues and eigenvectors of matrices. But a lot of the time, for the problem we are analyzing, we need some estimates or bounds on what the eigenvalues are, how large they are, how small they are, if they are kind of real numbers, complex numbers. And this is particularly useful, and you will see an example of this in the next homework. If the matrix you are thinking of is some sort of noise to the data. So what we really want to understand is how much does this noise affect our data? And this can usually be sort of controlled, or a lot of the times sort of just a rough estimate on the eigenvalues of this noise kind of matrix is useful. And a tool for kind of getting a fairly elementary estimate is what's called the Gershkorin disk theorem, or Gershkorin circle theorem. And so named because, let's say if you have a matrix of complex entries, then, and let's say we don't know anything about this matrix, may or may not be self-adjoint, etc. Then we still know, and if you remember the proof of our existence of eigenvalues for sort of operators between complex inner product spaces, or actually just spaces over complexes, not even inner product spaces. Then we said it always has at least one eigenvalue, and we can kind of repeat, and it has all n eigenvalues. And eigenvalues are elements of whatever field we are talking about. So in particular, if our matrices have complex entries, if the underlying field for the vector space is complex numbers, then eigenvalues are complex numbers. So the Gershkorin disk theorem or circle theorem kind of situates these eigenvalues in the complex plane. It says that the eigenvalues lie in one of these circles. So if you have an n times n matrix, it will give you n circles, and your eigenvalues will lie in the union of these n circles. So it's not saying that one eigenvalue will lie in each of these circles, by the way. It's not saying anything about how many eigenvalues lie in each circle. Okay. It's possible that maybe this circle contains 3 eigenvalues, maybe this circle doesn't contain any. Maybe this circle contains a lot of eigenvalues. So it's not really giving us a statement about sort of how many eigenvalues are in each circle. It's just saying that any eigenvalue lies in one of these circles. Okay. And this is kind of a more useful estimate if these circles are really small, and we'll see examples. Then we can get a fairly precise handle on what our eigenvalues are up to some small errors. Okay. And yeah, I mean, what I've drawn are kind of maybe more like potatoes, but these are just circles in the complex plane. Okay. Any questions about what we are trying to prove, or the statement of the theorem? There's also a fairly useful tool in an area called compressed sensing, and if we have time, we'll see an example of that. But let's just get to the theorem first, and this is just a formal version of what I was saying earlier, that if you have any matrix with complex entries, Then let's define these n circles. So let's define a radius, which is just the sum of the moduli of the off-diagonal entries. So the ith radius is just the sum of the absolute values or moduli of all the entries mij, which are not on the diagonal. So just exclude mii and take everything else. And let's now define the circle, which is just a circle with the center as the ith diagonal entry, and the radius as this ri, which we just computed. It's a circle in the complex plane, or it's a set of all complex numbers whose distance from the diagonal entry mii in the complex plane is at most the number ri, which we said was the radius. Okay. So, and the theorem just states that if you have any eigenvalue lambda for this linear transformation or for this matrix, it lies in one of these circles. So it lies in the union of these circles or disks. Okay. Any questions about the statement? I mean, the proof of the statement is very simple. It's just mostly understanding what the statement means, what it implies, how to use it is the interesting part. Also, just in case you know that the eigenvalues are real numbers, then what you are really looking at is the intersection of these kind of circles, if you wish, with the real line, which are just intervals. So if you know eigenvalues are real numbers, then it gives you a union of intervals rather than a union of circles. Okay. Okay. To prove it, yeah, as I said, so most of the interesting stuff is just sort of understanding what the statement is. To prove, let's say, so if lambda is an eigenvalue, then there exists an eigenvector such that m times x is equal to lambda times x. That is the definition of an eigenvalue. And moreover, x is not equal to 0. Okay. So x is a vector in C to the n. It's a vector of complex numbers. It's not 0. So some of its coordinates are not 0. At least one coordinate is not 0. So let's pick the largest one. So let's pick the largest coordinate. Okay. In absolute value or in modulus, if you're thinking of complex numbers. Okay. Or if there are two coordinates with equally large values, let's just pick one of them. So it's some entry with the kind of coordinate with the largest entry. And now let's just look at the equation we have. M times x is equal to lambda x. This is a vector equation. It's true. So we have every row of the vector on the right can be written in terms of the vector on the left. So in particular, if you look at the I0 row of both of these vectors, then on the left you have and on the right you have lambda times xi0. Okay. Now we know that xi0 is non-zero, so we can actually take it to the other side and divide it. And now we can write it So the special entry where you have I0 is multiplied by 1, and for everything else, we have mi0j xj divided by xi0. And we know that this is equal to lambda. Okay, and now a little bit of rearrangement gives us that lambda minus mi0 I0 is equal to summation j is not equal to I0 and now using so-called triangle inequality for complex numbers, and then we prove triangle inequality in more generality in vector spaces, but in complex numbers we know that the modulus of a plus b is less than equal to modulus of a plus modulus of b, and that the modulus of a times c is equal to modulus of a times modulus of c. So just using that, we get that absolute value or modulus of this is less than equal to we get the absolute value of the modulus of the off-diagonal entries, and the fraction that we have has modulus less than equal to 1 because of our choice of xi0 as the largest coordinate. So xj divided by xi0 has modulus less than equal to 1, which gives us the theorem. Okay. Any questions? And okay, so this was not about SVD or anything. It's just an application of the notion of eigenvalues, or it's just a tool for letting us understand where the eigenvalues lie. And it has a very nice application in this area called compressed sensing. So yeah, let me give a quick rundown of this application. In compressed sensing, what we are trying to do is again a sort of dimension reduction, but for a special kind of vectors. So we want to say that if we have a vector x, let's say in n dimensions or sort of a large dimensional space, we don't want to store the vector x, but we just want to store the vector a times x for some matrix A, which is kind of has many fewer rows than columns. So matrix A kind of looks like this, and x looks like this. So we get a kind of tiny vector when we multiply them, and this is the compression. And sensing just comes from the fact that this is used in some sort of sensors. In particular, there is this kind of notion of a 1-pixel camera, etc. So there are applications where you want to somehow compress the vector x and just store the few coordinates given by a times x. And in general, we can't do it for all vectors x. Now it's not just compressing some set of data points, but we are trying to compress an unknown x. We're just going to come up with this matrix A, which is sort of your camera. This x is the image you are seeing in the world, and this camera kind of measures or sort of takes some linear transformation of what you are seeing in the world and stores a few things in the memory. So here we are not trying to do this compression for all x, but for x which are sparse or which have only few non-zero coordinates. So in particular, vectors which have at most s non-zero coordinates is what we will call s sparse. And turns out that what you really need is, we want some notion of what it means for this measurement or this linear transformation A to preserve the information about this sparse vector X. So even if we store just A times X, we kind of have all the information we need. Turns out for the argument, it's sufficient to kind of just preserve the length and or the norm. And this already implies a lot of nice properties because A is linear. So if you are looking at X and Y, then it can also preserve the distance, or the distance of AX minus AY can be related to the distance of X and Y, maybe by multiplying sparsity by 2, etc. So we'll not worry about it, but it's sufficient to just preserve the length and approximately. So we'll say that it's kind of preserves it up to an error delta if the length, let's say squared, doesn't change by a factor of 1 plus minus delta. So it grows, it moves by 1 plus delta, or it shrinks by sort of no more than 1 minus delta. Okay. And this is what's called the restricted isometry property. Isometry is just preserving lengths. So the lengths would be equal. And here we are saying it's sort of an isometry because the lengths are almost preserved, but it's restricted because it's not preserved for all vectors, but only vectors which are sparse. And a lot of the time, the goal in compressed sensing is to design a matrix which has restricted isometry property, or to check if a given matrix has a restricted isometry property. The problem is it's hard to check this. So if I give you a matrix, it's not easy to check if it has the restricted isometry property. But it turns out what the Gershgorin circle theorem gives you is a simpler condition to check, which is very easy. And it implies the restricted isometry property. So a lot of applications, what they will actually do is say that my matrix has this stronger property, which is very easy to check, and it implies restricted isometry. And the way you kind of prove that this property implies restricted isometry is using the Gershkorin circle theorem or the disk theorem. And this property is what is called coherence, or the lack of it is called incoherence. So let's say if we have a matrix A with n columns, which are all unit vectors or length 1, then we measure its coherence by just saying how far are the columns from an orthonormal set. If they have k, if they are in k dimensions of the columns and there are n of them, n is larger than k, let's say, we are kind of thinking of matrices of this shape, then they can't all be orthonormal, but the smaller the inner product of any two vectors, the better it is, and we'll call this the largest inner product as the coherence. And what Gershgorin gives us is that if you have incoherence, or if mu is small, so incoherence just means mu of A is small, then you have restricted isometry property, or in particular, if you're going to look at S sparse vectors, then you have restricted isometry property with this parameter delta equals something, S minus 1 times mu. So if mu is sufficiently small, this is a small number. If mu is 0.01, S is 10, then delta is at sort of at most 0.1. So, okay. And the proof is just actually a couple of line applications of Gershkorin disk theorem once you just kind of state things the correct way. So again, what is the restricted isometry property? We want to prove that for any sparse vector S, X, which has at most S non-zero coordinates, the norm of A times X squared is kind of close to the norm of X squared. And let's just try to understand what this norm of A times X squared is. Let's say this set on which the entries are non-zero, let's call it capital S. And let's say it's just the first few columns. So let's look at this matrix restricted to these columns and let's call this A sub S. let's look at these entries, the non-zero entries of X, let's call them X sub S. Because all the other entries of X are zero, the norm of A times X square is equal to the norm of A sub S times X sub S squared, because all other entries of X are zero. So this is just, if you remember how a matrix vector multiplication works, this is just summation xi times ai, or the column vector ai. And if the entries outside the set capital S are zero, this is equivalently summation over I in S xi times the column vector ai. So the norms for A times X or A sub S times X sub S are the same. And then it's just, if we take the length of, which is also the length of X sub S to be 1, we just want to ask how sort of big or small is the length of A sub S times X sub S. And we already saw that this is the maximum eigenvalue A sub S star times A sub S. This is the same sort of computation we did for singular values a little while ago. And now let's just look at the shape of this matrix, A sub S times X sub S. So rows and columns are indexed by this set S. The diagonal entry is just the length of the ith column, which are 1. And every off diagonal entry is just the inner product of two columns ai and aj, where I is not equal to j. So every off diagonal entry is 1 minus mu times a. And then the Gershkorin disk theorem tells us that every eigenvalue lies, if lambda is an eigenvalue, then it lies in this now interval, because the matrix is matrix is symmetric or self-adjoint. So the eigenvalues lie in this interval where the radius or the size of this interval is just S minus 1 times mu of A. So the eigenvalue is very close to 1. Because the eigenvalue is very close to 1, the length of any vector is at most 1 plus some small error times the length of A times X is 1 plus some small error times length of X. You can check that the same is true for the lower bound. Okay, that's just one application of it. I'm sorry I went a couple of minutes over. Let me stop here. Yeah, feel free to ask me if there are any questions, and I'll stay on for some time after the lecture.